Hi everybody, back to our solid state electronic devices. So problem, this one going to be your for the problem, the homework number 4. We have total 9 problems. That's mostly from chapter 4, and for the first one, that's from chapter 3. Okay, your first problem. How long does it take an average electron to drift 1 micrometer in a pure silicon at an electric field of 100 volt per centimeter? And also repeat for electric field equal to 10 to the 5th volt per centimeter. B, repeat A for gallium arsenide at the electric field 10 to the 5th volt per centimeter. Assume the electron mobility, electron velocity is 10 to the 6th centimeter per second. Comment on the properties of silicon and gallium arsenide deducted from A and B. Okay, this problem, something about the drift velocity. You have a relation that your drift velocity equal to electron mobility. That's mu n in the unit of centimeter square per volt second, and multiplied by electric field, that with unit of volt per centimeter. Also for pure silicon from appendix 3 from the textbook, you have electron mobility is equal to 1350 centimeter square per volt second. First, start with electric field 100 volt per centimeter, that's low field. So your drifting time T equal to D over Vd, where D is 1 microsecond, micro centimeter, micron. That's the 10 to negative 4th centimeter. Vd you can find from this relation, where mu n, the electron mobility, is the 1350 centimeter square per volt second, and your electric field is the 100 volt per centimeter. This gives you 0.74 nanosecond for the drifting time. Now for electric field equal to 10 to the 5th volt per centimeter, that's considered to be a high field, and your velocity will be saturated. That's we call a saturated or scattering velocity. Then your drifting time, that's going to be d over Vd, but in this case Vd is going to be a saturated velocity, which is the 10 to the 7th centimeter per second. That's give you drifting time to be 10 picosecond. Okay, so for the same material, or silicon semiconductor, for the high field, it takes much less time than the low field, by comparing 10 picosecond to 0.74 nanosecond. Now what about gallium arsenide? Well, what the difference is that gallium arsenide, you have mu n, the electron mobility, equal to 8,500 centimeter square over V per second, volt per second, where for silicon you have your electron mobility equal to 1,350 centimeter square per volt second, right? Then for low field, electric field equal to 100 volt per centimeter, you end up with the drifting time to be 0.12 nanosecond. And compare, that's one for silicon, that's the 0.74 nanosecond. So in this case, you can see the difference, because this one is in the unit of nanosecond. For the high field, or electric field equal to 10 to the 5th, your VD is actually become saturated velocity, that's 10 to the 6th, and that's give you the drifting time to be 12.5 picosecond. And for silicon, you have 10 picoseconds. That's not much different for the high field, but for the low field, you can see this one is there are significant difference between the drifting time of silicon and gallium arsenide, right? So this is my conclusion. At low fields, transport properties of gallium arsenide are much better than those of silicon, but at high fields show no significant difference. That's the problem number one. Problem number two. For an arbitrary doped silicon semiconductor with an intrinsic carrier concentration in I and carrier mobilities mu n and mu p, that's for electron and this for hole, find the minimum possible conductivity sigma min. B, if mu n is greater than mu p, what kind of dopants in the term of donors, acceptors, or none should be introduced to the material in order to achieve sigma min, where sigma is the conductivity, right? Well, from the book, you can find the resistivity is going to be equal to 1 over Q, where Q is the electron charge, mu n, electron mobility, n, that's the electron concentration, plus mu p and p. And also at the equilibrium state, you know, np give you ni squared. So by plug in p equal to ni squared over n, and then you have resistivity in the term of electron concentration and electron mobility, as well as the whole mobility. To find rho maximum, you simply differentiate rho with respect to n and give you 0 for the maximum, right? Oh, sorry, this is for min, that's rho. And you can see that this equation will be 0 if mu n equal to mu p ni square over n square, or u n equal to square root of mu p over mu n ni, intrinsic electron concentration. Then you will be able to find rho min. Simply put n in this equation. Okay, this is your n, and this is your n. Finally, you will have your rho min, that's resistivity, equal to 1 over 2q ni square root mu n mu p. And your sigma min is simply equal to 1 over rho, right? That's your conductivity. That's equal to 2q ni square root mu n mu p. Now, B, for mu n is greater than mu p, you have to go back to the relation between n and ni. For mu p greater, hold on a second, I'm not sure. For mu n is greater than mu p, this one less than 1, right? So become n less than ni. To achieve sigma min, that means you need to dope more by acceptors, or acceptors Na need to be added to the system, okay, to have what? Sigma min. Next problem, problem 4.7, and anti-silicon sample with ND, that's donor concentration, equal to 10 to the 16th per cubic centimeter, is steadily illuminated such that GOP equal to 10 to 21st electron hole pair per cubic centimeter second. If tau n, that's the lifetime of electron, equal to the lifetime of hole, equal to 10 to negative 6 seconds for this excitation. Ask you to calculate the separation in quasi-Fermi level, or Fn minus Fp. Draw a band diagram such as figure 4.11. Okay. Now you have something to do with optical. Well, for the room temperature, you know Ni for silicon equal to 1.5 10 to the 10th per cubic centimeter. And since Nd much greater than Ni, because you dope with the silicon sample with Nd, right? That's the donor. So your Nd much greater than Ni. This is your Nd, and this is your Ni. Nd is in the order of 16, but Ni is in the order of 10 to the 10th, right? So your N0 about Nd, or 10 to the 16th per cubic centimeter. That's the N-type doping. And you will also be able to find P0 equal to Ni squared over N0. That's give you 2.25 10 to the 4th per cubic centimeter. So you already have N0 and P0. Now for delta N equal to delta P, that's the excess carrier. That's equal to GOP tau N, and that's equal to GOP tau P, where GOP is given. That's the 10 to 21st electron hole pair per cubic centimeter second. And this is your TP equal to Tn, that's 10 to negative 6 second. This gives you delta N equal to 10 to the 15th. So you start with what? Nd equal to 10 to the 16th, right? When you have optical or illuminated light on a silicon sample, your delta P is increased very quick and become a large number, right? Because you have only ND doping, not Na. Now N equal to N0 plus delta N, you have N increasing from N0 to N0 plus delta N. Thus you have the new electron concentration to be 1.1 10 to the 16th per cubic centimeter. This is unperturbed. And your P equal to 10 to the 5th. As you can see that your P increased by many orders of magnitude, right? Because when you start, you had no Na or acceptor. Now you apply this equation to look for Fn minus Ei quasi-Fermi energy level. Let's give you 0.35 electron volt, same as the Ei minus Fp for a p-type semiconductor. You end up with Ei minus Fp equal to 0.288 electron volt. Then you can find the gap between Fn and Fp. Simply add two equations together. So you end up on the left become Fn minus Fp, and on the right become 0.35 plus 0.288. That's give you 0.638 electron volt. You also do an alternate calculation simply by multiply N and P together. That's give you Ni squared exponential Fn minus Fp over kBt. And you get exact number to be 0.637 electron volt for the gap between Fn and Fp. So this is your energy band diagram. You have Ec, you have Ev, you have Ei. At the middle of the band are gap energy, and your Fn is the 0.35 electron volt above Ei, and Fp is the 0.288 electron volt below Ei. Next, problem 4.9. The direction of the built-in electric field can be deducted without math by sketching the result of a doping gradient on the band diagram. Starting with a flat Fermi level at equilibrium, place Ei near or far from Ef, as the doping is varied from the two cases of a gradient in donor or acceptor doping, as in example 4.5. Show the electric field direction in each case based on equation 4.26. If a minority carrier is injected into the impurity gradient region, what direction is it accelerated in the two cases? This is an interesting effect which we will use later in discussing transistor. Okay, they want you to consider the electric field direction for n-type doping and p-type doping. Wherever for the n-type, this is your energy band diagram, and this is for p-type. This is your energy diagram. You have Ec, you have Ev, you have Ei. And since you know that E is directional proportional to the change of the energy with respect to x. So you can see this one is the positive slope, right? Or this one simply slope. Actually, I should write this down as E, that energy from the left plot. So that's give you an electric field in the positive direction, and it's constant because this linear energy band diagram. And for a p-type acceptor, the slope become negative, so that's give you E to be a negative direction or negative x. This is the conclusion. When minority carriers are injected into the impurity gradient region for entire material, okay, and you know that that's the minority carrier is whole. And you have hole moving from the left to the right because F equal to QE, where E is there in the positive direction, right? Q for the hole is positive charge. For p-type, you know that your E is moving from in the direction of the right to the left or negative x. But your Q, this is your minority carrier, is electron, so the charge become negative. And that's also give you the force to the right. So carriers will be accelerated to the positive direction in both cases, for both in the type semiconductor and the p-type semiconductor. See next page is 31. Problem 4.12. For a steady state minority hole distribution shown in figure 417, find the expression for the whole quasi-Fermi level position, or EI minus Fp, while Px much greater than P0. On a band diagram, draw the variation of Fpx. Be careful when the minority carriers are filled. For example, when delta P is an I, Fp still has a long way to go to reach EF. However, they ask you to plot. First, I ask you to look for the expression for quasi-Fermi level, or EI minus Fpx, while Px much greater than P0. Well, we start from for the anti-doping, you have an equation of p-type and n-type, right? We worked out on that before. For the p-type, you have EI minus Fp equal to these expressions. And for n-type, you have Fn minus EI is equal to this expression. But now let's consider for the whole. You have P equal to P0 plus delta Px, where your delta Px is the exponential excess whole distribution. Then you plug in P in this equation. But since your Px much greater than P0, so you can ignore P0 here. What you have left is the delta Px. That's why I have this expression. Okay? Where your delta Px equal to delta P exponential negative x over Lp. And you can see that your EI minus FP depend on X are according to this expression. This is your X. And you can notice for X equal to 0, this term drop. You have only this term left, right? So that's why I have starting at X equal to 0. This is X equal to 0 for the plot. I have EI, the gap EI and FP become KBT ln delta P over Ni, this term. And FP going to be plot going to be linear according to X. Okay, so FP actually depend on X. This is what the energy band diagram that you have for the quasi Fermi level, and this is your delta P equal to delta P exponential negative X over LP. Okay. Problem 4.13. Assume an entire semiconductor bar is illuminated over a narrow region of its length such that delta N equal to delta P. That's our excess carrier concentration in the illuminated zone, and excess carriers diffused away and recombined in both directions along the bar. Assuming delta N equal to delta P, sketch the excess carrier distribution, and on a band diagram, sketch the quasi Fermi level Fn and Fp over several diffusion lengths. From the illuminated zone, see the cautionary note in problem 4.12. Well, this is you have a semiconductor bar, and you illuminate light on the bar. They want you to plot, sketch excess carrier distribution. So we start with the excess carrier distribution, delta Pn x. You look for this the expression for delta Pn x. Well, from the minority carrier distribution equation, you have these expressions. Under steady state condition with GL equal to 0 for x greater than 0, and we are not interested in the time domain, so this term drop out. You have only two terms left. That's become equation number 1. Now you need to solve the differential equation for delta Pn. This is your solution. A exponential negative x over Lp plus b exponential x over Lp, where Lp equal to square root of dp tau p, the lifetime, okay, we will talk about this tau p. I'm not sure that we talk about that, but let's move on. All right, we come back this one later. Now you need to apply boundary condition. For the boundary condition, you know that delta Pn at x equal to 0 have to be equal to delta Pn at x equal to 0. That's equal to delta Pn 0. Okay. And also for x go to infinity, you have no excess concentration. So from the solution, you apply the boundary condition. First, start with x go to infinity. You end up with this term because this term drop rate. But you want this one to be 0, so you'll be have to be 0. Sorry. So you can ignore this term. The second boundary condition, delta Pn at x equal to 0, equal to delta Pn 0, right? So that's equal to A. This is your A. Finally, you have an expression for delta Pn at arbitrary x equal to delta Pn 0 exponential negative x over Lp. From the expression, you be able to sketch delta Pn x and x, and you have an exponential decay. Excess carriers diffuse and recombine, decaying exponentially away from illuminated region. Okay, this is the illuminated region, and this is your quasi Fermi levels varying very linearly outside the excitation region, while delta P much greater than P0. And I also confirm this by applying this equation. So your AI minus AP, this is you want to plot your AP, right? And that's enough with proportional to x, and become a linear plot where Px much greater than P0. Problem 4.14. The current required to feed the whole injection at x equals 0 in figure 417 is obtained by evaluating equation 440 at x equal to 0. The result is the xp at x equal to 0 equal to qa dp delta p over lp. Show that this current can be calculated by integrating the charge stored in the steady state whole distribution, or delta px, and then dividing by the average whole lifetime tau p. Explain why this approach gives ip x equal to 0. Okay, let's take a look. They want you to find the current by integrating the charge stored in the steady state whole distribution, or delta px. But from equation 4.14, I actually pick up this equation from the book to also be able to find IP starting from this equation, or equation 4.40. But they want you to find the current from by integrating the charge stored in the steady state whole distribution. Okay, so this is your plot between px and x, and your p equal to p0 plus the excessive charge, which is the delta p exponential negative x over lp. We did that before. Now for the charge q, let's start from here. It's become actually the area under the px and x plot. Your dq simply become q px dx, the chart multiplied by px dx, and your px, since your px much greater than p0, so you drop p0, you end up with the earlier delta p exponential negative x over lp, and you multiply by the area. So your q, simply do the integration from 0 to infinity of delta p exponential negative x over lp, and you end up with your qp equal to aq delta p lp, and your current simply equal to q over tau, qp over tau p. This is your q, and this is your tau p. And you also using the relation lp, that's the diffusion length lp, equal to square root of dp tau p, then your tau p equal to lp square over dp. You simply plug in your tau p in this equation. You end up with ip equal to q delta p dpa over lp, same as the you derive from equation 4.40. Okay. Okay, the last problem for the homework number 4. With EF located at 0.3 electron volt below the conduction band in a silicon sample, what charge state would you expect for most gallium atom in the sample? See figure 4.9. What would be predominant charge state of Ni, Au, doubt bi-charge state with mean neutral, singly positive, doubly negative, etc. Okay, you need a figure 4.9 from the textbook. Starting from the band energy diagram, you know the energy band gap of silicon is about 1.11 electron volt, and this is your EC, this is your EI, this is your EV, and you have what? EF located 0.3 electron volt below the conduction band, so this is your EF. Well, from the figure 4.9 in textbook, you can see that GA are singly negative located at the energy 0.065. So you pick up GA here. For Ni, when you look for your EF, Ni is somewhere doubly negative charge, somewhere here, and Au also, this is your energy 0.54, but since the EI is equal to 1.11 or Eg over 2 energy band gap, the half of our energy band gap, that's 0.55 electron volt, so it's somewhere around here. That's give you Au singly negative as shown in the figure 4.9. You go back to the textbook, you will see that clearly. Okay, that's all for the homework number 4, so problem. I'll see you in the next series then. Bye.